This is a how to complete bond calculations video, and I'm going to show you a few different examples. And there'll be an opportunity twice for you to pause the video and try and complete one on your own. So just to have a quick recap in case you can't remember what's going on when we're looking at a bond energy calculation. When a chemical reaction takes place like this one here, where we've got methane reacting with chlorine, what happens is all of the bonds in the reactants here break, which is an endothermic process, and then all of the bonds in the products over this side form, and that's exothermic. So let's say that again, all of these bonds in the reactants break, so all the bonds there break, endothermic, and all the bonds over here have to form, which is an exothermic process. And then what determines whether the chemical reaction is exothermic or endothermic overall depends on which of these two values is greater. So the first example here, in the exam question you'll always be given these bond energy values here. The exam board do not expect you to know those off by heart, they'll always be given to you. Every example I'm showing you here I have made more difficult because I haven't drawn out the bonds for you. Now quite frequently in a question they will draw the molecule to help you, but I haven't done that, but we can do that as we go along. So this is our first example. The first thing to do, if they haven't done it, is to draw it out for you. So we've done alkanes now, so you should be happy that methane looks like this, and it's reacting with a molecule of chlorine, and it's forming this, what's called a haloalkane or a halogenoalkane, and hydrogen chloride. So that's what's happening. So the first thing we're going to do is focus on this side of the equation, the endothermic bond breaking. And all we have to do is count how many of each bond is being broken. So you can see I have 1, 2, 3, 4 carbon-hydrogen bonds, and the table of data tells me that each one requires 413 kilojoules per mole of energy to break. So I'm going to do 4 lots of 413 for the methane molecule, and then the only other bond I've got left on the reactant side is this chlorine-chlorine bond here. So I've got one lot of 243, and we just add those together. So that's 1652 plus 243 is 1895 kilojoules per mole. So that's how much energy is taken in to break all of those bonds in the reactants. And now we need to work out how much has been given out making the bonds in the product. So this time I've got 1, 2, 3 carbon-hydrogen bonds. So it's going to be 3 lots of 413. And I've now got 1 carbon-chlorine bond that I didn't have before. If I look in my table, I can see that a carbon-chlorine is 327 kilojoules per mole. And I've got 1 hydrogen-chlorine bond, which is 432. So again, you just do the maths and add those up. 1, 2, 3, 9. Okay, 1998 kilojoules per mole. So what I can see straight away without finishing the equation off is that more energy is being given out than was taken in. So I can already see that this is going to be an exothermic process overall, because this number on the right hand side is larger than on the left hand side. If you'd got to this point in the question, you'd probably be getting a couple of marks at least, possibly 3 for working out these two values. But I need to finish the equation off for the overall energy change, which is just going to be this number minus this number. So the first number that I've calculated, take away the second number that I've calculated. So 1895 minus 1928. So it's minus 103 kilojoules per mole. So that's my answer. That's going to get me the final mark in the calculation. When you look at the mark schemes for these, quite often the exam board will say to ignore the sign. I would say definitely include the sign, but if you've got it wrong, they won't penalise you for that. And what I can see, as we just said earlier, because this side is bigger, I've got a negative value. And hopefully what you can remember is that if the value is negative, it means it's an exothermic process overall. Okay, so if we turn over, this is an example for you to have a go at. So here you've got, is that right? Yes, I did mean that. Did I mean that? Yes, I did mean that. No, I didn't mean that. That should be C2. Apologies. We've got ethene reacting with bromine. Now this reaction here we've actually learnt about because this reaction is the test for unsaturation. So the ethene molecule reacts with the bromine and decolorizes it. Again, you've got your table of data over here, and then we just need to draw out what's happening. Like I say, the exam board more than likely would have given this for you. They wouldn't expect you to draw it out, but so we know. In fact, I'm going to do it under here so we've got a bit more space. Okay, so you can see that the ethene molecule is reacting with the bromine and forming, again, this is called a halogenoalkane or a haloalkane. And the double bond here is broken. That's how these two have added on. And that's why the bromine loses its orange colour when you put it into the alkene, because it doesn't exist anymore. It's now formed a different compound. But like I say, they would more than likely have drawn that out for you. So what I want you to do is pause me, use the values, I'll just push that up slightly so you can see, use the values in that table to calculate the overall energy change. Now one thing to be aware of, and this is where some of you lost marks in the homework that we set over lockdown, is just be aware this is a carbon-carbon double bond, this is a carbon-carbon single bond, and if we look at the table of data, they have two very different values. So don't forget when you're using this one here, we use this top value because it's a double bond, not a single bond. All right, so pause me for a second and then have a go at calculating that. Okay, I'm going to show you what you should have got as your answer now. I'm just going to move this up like this so that you can't see the values, but hopefully you had them in front of you from a second ago. Okay, so what we're doing here, well, I've got one carbon-carbon double bond, which the table tells me is 614. I'm adding on to that 1, 2, 3, 4 carbon-hydrogen bonds, which are 413. And I'm adding on a bromine-bromine bond, which is 193. Now you'll see that I put lines through the bonds once I've included them in the calculation. That's just my way of double checking that I haven't missed anything out. And particularly if you get a more complicated one with lots of bonds, it makes that a much easier process. So over this side, we've got 614 plus 1652, 193. 2459 kilojoules per mole. Okay. Then over this side, I've got a carbon-carbon single bond this time, which is 348. I'm adding 1, 2, 3, 4 carbon hydrogens again. But this time, I've also got 2 carbon-bromine bonds, and they're worth 276 each. So that's 2 times 276. Sorry, paper's sliding all over the place. Okay. Okay, so you should have got those two values. And like I said in the previous question, straight away I can see that the exothermic bond making side is a greater value than the endothermic bond breaking side. So straight away I can see that this is going to be an exothermic reaction overall. But I need to prove it, so I'm going to do 2,459 minus the 2,552. And it's minus 93 kilojoules per mole overall. So I can see that it's an exothermic process because it's got a negative sign. Hopefully you got that answer when you did yours. Okay, so we've had a look at two examples of exothermic. So let's look at endothermic now. So here you've got the decomposition of hydrogen bromide. So hydrogen bromide decomposing into hydrogen and bromine. And there's our values. And here we've got 2 HBr going to hydrogen, hydrogen plus bromine, bromine. Now this is an interesting one because we've got a multiple here which we haven't had yet. So if you do get a multiple, whatever that value is, 2, 3, 10, whatever, I would draw out that number underneath. I'm actually going to cross that out and just draw myself a second one underneath so I know to include it. Put my dividing line. So over this side I've got 2 hydrogen bromine bonds, which is going to be 2 lots of 366. And then over this side I've got 1 hydrogen hydrogen, which is 436, and 1 bromine bromine, which is 193. So it's 732. 436 and 193 equals 629. Now, unlike the previous two calculations, I can see that straight away the endothermic side is a larger value, so I can see that this process is going to be endothermic overall, and I just need to prove that to get an overall value. So I'm going to do the same again, 732, my left hand side number minus my right hand side number. And I get plus 103 kilojoules per mole. Now I would encourage you to include that positive sign. Don't just assume that because you haven't put a negative that it's a positive value. Make sure you include it. But we can see that, yeah, it's endothermic overall. Okay, so finally then, another one for you to have a go at. So there's our values. And this time we've got nitrogen and oxygen reacting to produce nitrogen monoxide. I'll draw this out for you because this one is slightly complicated. It's got a triple bond, so the nitrogen is triple bonded to another nitrogen. That's reacting with a double bonded oxygen, and it's, oh, what am I doing? It's forming 2 N O. Again, I've got 2 here, so I would cross that out and put the O underneath it. Okay, so pause me and have a go at doing that calculation. Okay, so over this side, straightforward, I've got 1 triple bonded nitrogen to nitrogen, which is 945. Hopefully you can see that when we've got more than a single bond, if it's a double or a triple, the values tend to be a lot bigger. So we've got 945 plus 1 oxygen to oxygen, which is 498. And then over this side, we've got 2 lots of nitrogen oxygen, which is 630. On that side, and bear with me, 945 plus 498 is 1443. Again, I can see that this side, the endothermic bond breaking side, is a larger value than the exothermic bond making side. So I can see it's endothermic straight away. But again, need to prove it. So I'm going to do left hand side value minus my right hand side value. Plus 183 kilojoules per mole. So again, I've got a positive value, so I know that it's endothermic. To pull that down for you so you can see. The only other way I've seen the AQA change this question is that they give you some of the bond values. So they maybe give you this one and this one, and they give you the overall energy change, and then they ask you to calculate this. And then you're just going to treat it like you would an algebraic equation in maths. So you would say, so I've got 1443 plus 2 lots of x, because I don't know what's going on this side, is equal to plus 183. And then you could just rearrange it to get yourself what x is worth. So that's the other way of doing that question. Okay.